Firstly, thank you for the organizing committee to giving me this chance to present my work. I'm Kusumpal Yadav, working under the supervision of Dr. Devjyoti Mukherjee in Indian Association for the Cultivation of Sciences. Yesterday, my supervisor has already discussed when there will be a metal oxide interface, we usually observe a giant topological Hall effect. So, I will discuss one of the presented work in a more detailed way, where we have observed a giant topological Hall effect in multiferroic thin film structures. Firstly, Hall effect, we know that when we place a current carrying conductor inside a magnetic field, there will be a transverse voltage generated. In case of ordinary Hall effect, the generated transverse voltage is proportional to applied external magnetic field. Where in case of ferromagnetic thin film, the generated transverse voltage is proportional to the magnetization of sample. Recently, due to some non-trivial spin textures, there is an additional contribution to this effect that is known as the topological Hall effect, and that can arise due to interface or non-cytosymmetry in the system or some geometrical frustration. And the application of this topological Hall effect is for low power. Using this, we can make low power consumption and high speed data storage devices. This can also be used in magnetic field sensors and neuromorphic computing and quantum devices. The structures that I have grown is that initially I have taken permalloy, which has n-type carrier, and grown on LSMO, which we have that is a p-type carrier. So when we grow permalloy on top of LSMO, there can be an interface electric field that can tune this anomalous Hall effects. And then what we have done is that we have decoupled these with a ferroelectric BTO layer. And the reason choosing all this is that they have also a closed lattice mismatch, so we can epitaxially grow all heterostructures. During the growth, we have using the reed, we have optimized the system, and here we can observe that we have obtained a continuous stick-like patterns which show a good epitaxial thin layer by layer thin film growth, and also we have obtained these oscillations which show one oscillation corresponds to the growth of one monolayer. And using these reed patterns, we have also calculated the in-plane lattice parameter. Then from XRD, we have confirmed that epitaxial growth of thin film. Here you can observe that all layers grow parallel to that of the substrate, which shows an epitaxial thin film growth. And further, we have confirmed the orientation growth by measuring the phi scan. And you can observe that the peak we have obtained are at an interval of 90 degree, which shows a fourfold cubic symmetry and cube on cube epitaxial thin film growth. And also we have done the rocking curve, and from there we have obtained the full width half maxima that is less than 0.1 degree, which show a good crystallinity thin film growth. Further, we have confirmed the epitaxial thin film growth and also calculated the in-plane and out-of-plane lattice parameter by using the RSM, and that we have done around an asymmetric plane. And here we can observe that we have, corresponding to a single layer, we have obtained a single peak which shows a good epitaxial thin film growth. And from there we have calculated in-plane and out-of-plane lattice parameter. And we have observed that permalloy grown on MGO has a larger tetragonal distortion in comparison to permalloy grown on BTO. And from there you can observe the out-of-plane in-plane lattice parameter. Then we have studied the surface anisotropy using the longitudinal MOC. And from what we have done is that we have rotated the sample, and by rotating the sample we have measured the corrosive field and the carry ellipticity, and there is no we have obtained just a circular, so there is no anisotropy, surface anisotropy in the thin film, which shows that the surface is similar in all the heterostructures. Then using the PPMS, we have studied the out-of-plane, and you can see usually when we take two ferromagnetic thin films, so there is a high chances that one behave as a soft ferromagnetic layer, another behave as a hard ferromagnetic layer. And if there is no magnetic interaction at the interface, so the corrosive field that we have obtained for the heterostructure should be similar to that of the soft ferromagnetic layer. But what we have observed in permalloy LSMO, that the corrosive field that we have obtained is much higher in comparison to single permalloy and LSMO layer, which shows that there is some magnetic interaction going through this permalloy and LSMO layers. And as we have decoupled these layers, the corrosive field that we have obtained is similar to that of the single LSMO layer. Then we have studied the Hall effect, and here we can observe that the positive slope shows the p-type carrier and negative shows the n-type carrier. This has the whole contribution from ordinary anomalous and the topological, where we have using the linear spore we have separated out the ordinary part, and the anomalous is proportional to the magnetization. So this has the contribution of anomalous plus the topological part. Using out of plane magnetization, we have calculated the anomalous Hall effect, and from there we have subtracted out the topological Hall effect in all heterostructures. What we have observed, a small topological Hall effect in permalloy, and there is no topological Hall effect in single LSMO layer. But as we have grown the heterostructure, there is a large change in the topological Hall effect. That can be due to the inbuilt electric field that can give rise to a Raspa type spin orbit coupling that can fuse the topological Hall effect. And also, in case of permalloy BTO LSMO, we again observe a large change, and this can be due to that BTO is inbuilt ferroelectric, and as we have grown epitaxially, the strain increases, and that increases the interface electric field. So again, which can leads to a Raspa type of spin orbit coupling. Then to understand this effect, we have collaborated with Dr. Sayantika Bhowal, and using the tight winding model, they have calculated the topological Hall conductivity, which is quantized in nature, which shows the carbonic crystal. And then what they have done is that they have introduced the Raspa spin orbit coupling, which tunes this topological Hall conductivity. So this shows that the increase in the topological Hall conductivity in the heterostructure can be due to this Raspa type of spin orbit coupling. Also using the MFM, we have observed this non-coplanar spin textures. This red one shows the positive z direction magnetization, and blue one shows the negative direction of magnetization. As we have increased the positive magnetization, more and more spin get aligned in the positive direction, but there is some isolated nanodomains form, which shows the presence of non-coplanar spin textures. And we have done for all heterostructures, and we have observed in all heterostructures. And the main point that is that we have obtained this effect at a room temperature and at a very small field, so which makes it a high system that can be used for spintonic devices. And also we have studied the temperature dependent, which shows the temperature dependent Hall resistivity at all higher temperatures also. So finally I will conclude that we have obtained the large anomalous and topological Hall's effect in heterostructure using the Raspa type of spin orbit coupling, and this system can be used for the future spintonic devices. Finally, I will acknowledge my professor Dr. Devjyoti Mukherjee and Dr. Sayantika Bhowal for the theoretical work, and Professor Tapu Vartasam for the MFM, and my lab mates. Thank you.
Thanks for the nice talk. Any questions? Any questions? Especially from the students? Yeah.
I have the same question which I was actually asking yesterday, that NGO you were growing and also you were using LEO, and you are saying that it is really...
Actually, in this work, I have only used MGO, yeah. But I can answer your question.
Like you have introduced that, the NGO, and
if we use LEO substrate, so when we grow LSMO, there will be in-plane compression in the LSMO. So then when we grow this BTO, so the lattice mismatch increases, so there will be large tetragonal distortion in the BTO. So that will introduce large polarization value in the BTO. So that can also affect, and that is the next work that we have done.
My another question is, as per my knowledge, STO is the best substrate to grow the LSMO because the lattice mismatch is really less there, and you will get really less disorder or something.
Actually,
like
that is the reason that I have choose this MGO and in another work LAO, because when we grow on STO, LSMO does not have large mismatch. So the strain will also be smaller in the LSMO. And when there is a change in the strain, that if we have in-plane compression and out-of-plane, in-plane compression, so the MN bonding that decreases due to strain, and that can affect the property of this BTO. And in another case, if we have compression, so the MN bonding will be increased in the the compression will be in the in-plane direction. So the hopping will most probable through the in-plane direction, and the out of plane there will be less probability, and that can means this. There is a study which shows that if we change this strain in the LSMO, the BTO polarization we can tune by 180 degree in the polarization.
Yeah, but still, like MGO and LSMO is really far if you will see the strain.
Yeah, that.
So what happens when you will grow a little bit thicker film, it will be relaxed.
Yeah.
Sometimes. So like whatever is happening in the interface of the substrate and the thin film, same disorder or distortion is happening in the BTO LSMO that side.
Yeah.
Like I'm doubtful about this thing.
Actually, in next work we have also done the TM, and that yesterday my supervisor has shown us, and where there you can observe that there is LSMO BTO, there is no interfacial defects from the TM images. There is some as we increase the thickness, but to study this property we required strain. If there is no strain, then there is no point of doing that.
Thank you so much.
Let us thank the speaker again.
And I am a PhD student at IIT Kanpur. So today I will be talking about fermi-liquid behavior and characteristic temperature dependent susceptibility in clean ReO2 single crystal. So magnetic material generally classified into two phases, ferromagnet and antiferromagnet. There is a new class of magnetic material which is introduced that is named as altered magnets. So I am not going to detail about this thing because of the time limit. So among the various proposed material, ReO2 is one of the most attracted candidate because of the large spin splitting, the order of 1.4 electron volt, and that produces a large anomalous Hall effect. But there are some conflicting reports in 2024 on the existence of the magnetic ordering on this single crystal. So nature of the magnetic ground state in this system is still under debate. So this there might be issue of the crystal quality and crystal quality. So one of the important parameter to check the crystal quality is residual resistivity ratio, which varies widely. From older studies 1960 to 1980s, this number varies between 80 and 800, and most recent studies related to the altered magnetism on ruthenium oxide thin films, this number varies 3 to 11. So it is highly desirable to grow such high quality single crystal of ruthenium dioxide and investigate the intrinsic and magnetic properties of this system. So these are some current issues I am going to discuss in this presentation. So to grow this ReO2 single crystals, so we use a sublimation transport method and ReO2 as a starting material, and to improve the crystal quality and reduce the contamination, we use a latex rubber sleeve to make this kind of compact rod instead of using metal jig. And so some of the key issues are also written in this paper, which is published in 2025. And to grow such crystals, so expensive 2-zone or 3-zone furnace is not necessary. Our modified single zone furnace can capable enough to grow such high quality and large crystals. And using this necking shape crystal growth tube and finally tuning the crystal growth parameters, we can easily grow the large size and high quality crystals. So we observe a systematic variation of the sublimation temperature and systematic variation of the crystal morphology. So we obtain a flat crystals up to 10 mm long, columnar crystals, needle-like crystal, fiber crystal, as well as some twin crystal at high temperature. So now this crystal orientation are identified using this Laue pattern and XRD. Intense Laue patterns also suggest the high quality crystals. Now as I said, one of the important parameter to check the crystal quality is the residual resistivity ratio. For that we measure the resistivity using the AC 4-probe method using a lock-in amplifier, and a frequency of 17 Hz is used to measure the to suppress the noise level to a negligible level at low temperature. And at low temperature the resistivity of ruthenium dioxide is very low, so it is very challenging to measure accurately this residual resistivity. For that we attach the current lead at the both end of the crystals and the voltage lead at the side surface of the crystals, and with a separation of the different voltage leads. So you and this current leads and voltage leads are attached with the silver epoxy at cured at 500 degrees centigrade to evaporate the epoxy content. That will actually reduce the contact resistance, and this will also give us the robust contact leads. And we obtained a very low resistivity around 30 nanohm centimeter, and the residual resistivity is higher than 1200, and different electrodes also getting the same results. So also different morphology crystals we obtained a similar results, and this is quite reproducible. Now we measure the thermodynamic properties of the system. For that we measure the specific heat at a zero field, and this is a C over T versus T square plot with some previous literature data. And if we look, you can see that the previous literature there is a nuclear quadruple contribution at low temperature, but we didn't observe such behavior, and this is also consisting with the some of the reports, NMR reports. And if we try to fit this experimental data with the power law expansion gamma T plus beta T cube, and these are the some corresponding gamma, beta and D by temperature values. And if we apply magnetic field at 5 Tesla in a field along 101 direction, so no significant field dependence can be observed up to 5 Tesla. And there is no significant anisotropy also present in this system when we apply the field in 3 different directions. Now what about the magnetic properties? So for that, so 2 important measurement, one is the quantum oscillation measurement, another one is the RPS measurement is done on this high quality crystals. So this and both of them verify that this high quality ruthenium dioxide single crystals are no longer altermagnet or paramagnet. This is a pure no longer altermagnet or antiferromagnet. This is a pure paramagnet. So this quantum oscillation measurement is performed in Cambridge University by Professor Eaton's group, and the RPS measurement is performed at Tohoku University by Professor Sato's group. And one of this paper is published in PRX in 2025. Another one is published in PRB this year, and both of them used our crystal with RRR 400. Now such crystals shows characteristic susceptibility behavior. So this is the M over H versus T for this ReO2 crystal, RRR 400 and 1200, and with decreasing the temperature this susceptibility decreasing, and low temperature there is a significant upturn. So this low temperature upturn corresponds to the paramagnetic impurity. And one interesting thing that with increasing or higher quality crystals, this low temperature upturn is significantly smaller. And if we try to fit it with up to 30 Kelvin using this Curie law equation, and we obtain the impurity concentration around 36 and 15 ppm for RRR 400 and 1200, which is significantly low. So we can say this is a kind of ultra clean single crystals. And if we compare with some other reports, this low temperature upturns also significantly lower in our sample. These are some comparison table. Now if we measure it in a 3 different field direction, so this is the M over H versus T at 3 different field direction. There is a weak magnetic anisotropy, about 15% is observed, and anisotropy is mainly dominated by the chi0 term. Now one interesting thing that the paramagnet generally the susceptibility decreases with increasing the temperature, but here for the ruthenium dioxide what we observe that susceptibility increases with increasing the temperature. To look into such behavior, we try to fit up to 400 Kelvin this experimental data using equation 1 and equation 2, but it deviates significantly above 30 Kelvin. So then we try to another equation, this equation 3 with adding T square log T term. This also fails to explain the experimental data. So this equation 3 is generally used for the spin fluctuation system. Now we use another phenomenological logarithmic T dependence, which is adding another term T log T over T0 term. Now question is what are the physical meaning of this extra term? So does it really mean anything about the energy dependence of the density of state? For that we check the density of state of this system with a U equals to 0, and that gives a non-magnetic or paramagnetic ruthenium dioxide system, and in the vicinity of the Fermi energy, this shape is convex upward. And if we consider this shape, so this actually tells that the average or density of state is reduced with increasing the temperature. Now if we try to calculate the spin susceptibility for a non-magnetic metal using this equation 5, which tells the average over density of state, and what we obtain, the susceptibility decrease with increasing the temperature, but we obtain that susceptibility increase with increasing the temperature. So this is contradict with the experimental result. So we go with the another mechanism. So generally there is a this kind of behavior also observed in the titanium, other transition metals, and there they explain it with the lattice expansion induced variation of the orbital paramagnetism, where the total susceptibility is Pauli susceptibility, orbital Vomlak, and core diamagnetic. And if we look into the susceptibility at a different field, that is explained by a term with the h square log h over h0, where h0 is the characteristic field. So overall total characteristic and temperature and field dependent susceptibility for ruthenium dioxide is 4 contribution term: Pauli susceptibility, Curie term, lattice expansion induced orbital paramagnetism, and field dependent contribution in chi. Now if we look into the universal plot, so this is the Wilson ratio, one of the important parameter to check the location of the this ruthenium oxide. So Wilson ratio is the ratio between the chi 0 and gamma, and Rw is 1 for the free electron gas, 2 for the strong electron system, and 2.3 for the ruthenium dioxide. This is higher because some orbital paramagnetism contribution is enhanced this Wilson ratio higher than 2. Ruthenium dioxide is not a strongly correlated system. Now there is another universal plot which is called Kadocki-Woods ratio. This is from the transport perspective. What is the ratio plot? This is the log-log plot of A over gamma. Gamma is the Sommerfeld coefficient, and A is the resistivity coefficient of the T-square term, and this is the 0.2, and with increasing the crystal quality, this is moving towards the free electron gas. So that means this ruthenium dioxide is a weakly correlated Fermi liquid system. So to conclude my work, so we obtained a large ultra clean ReO2 single crystal with a crystal with RRR is higher than 1200, and high quality ReO2 single crystal show a clear paramagnetic behavior, and there is no trace of altermagnetism. And temperature and dependent susceptibility is well fitted with T log T over T0 and H square log H over H0 terms, and the characteristic temperature dependent susceptibility with anisotropy is attributable to the lattice expansion induced variation of the orbital paramagnetism. And last, ReO2 behaves as a 3-dimensional weakly correlated Fermi liquid with a modest electron interaction. So finally, I would like to thank all of my collaborators, and I would like to thank especially my supervisor, Professor Chanchal Saw, and Professor Yoshithiri Mayano, the professor from Kyoto University, who are helping me to complete this project. And finally, I would like to thank all of you for paying attention. Thank you.
Thanks for the nice presentation. So, any questions?
Thank you for the presentation. In the slide where you showed the quantum oscillation and the RPS data, so there you mentioned something about that previous studies claimed that this sample was altermagnetic or antiferromagnetic, but from this data you are sure that this is a pure paramagnet. So can you just explain why, how can you say from this data?
Okay, first of all, this quantum oscillation and RPS measurement is, so this is the experimental data, and this is also the experimental data. This is the Fermi surface. So, it's not visible quietly. So, if you look into these solid lines, so this figure B is the theoretical calculation for the paramagnetic system. And if you look into the, if it is antiferromagnets, so it should be behaves like this. So this experimental data and theoretical data closely matches with the paramagnetic system, and similar things also the quantum oscillation measurement. So this experimental measurement, when the field is applied from 100 to 001 direction, and the whatever Fermi surface we obtain, which is nicely matches with the theoretical calculation for the paramagnetic system. So this is the two vital confirmation. So this high quality Ru2 single crystal is a paramagnet.
Thank you.
Okay, so any other? So if not, let us thank the speaker again.
Thank you.